Hello everyone, welcome to MP Coding. Today, I am going to show you how to set up and generate a PWM signal using a microchip dsPIC33 microcontroller. I will be using MCC Melody to configure everything inside the project, so you don't need to write any register-level code manually. For this tutorial, I am using a dsPIC33 development board. With the chip dsPIC33 CH512MP508. And for programming and debugging, I am using the PICkit 5. In this video, I will walk you through 4 examples. The first example, 10 kHz with 50% duty cycle. The second example, 10 kHz with 30% duty cycle. The third example, 100 kHz with 40% duty cycle. And the fourth example, PWM output using DMA, where the duty cycle automatically changes every PWM period without any CPU involvement. Alright, let's get started. For the development environment, I will be using Visual Studio Code with the MPLAB Extension pack installed. If you don't install the MPLAB Extension pack, or if you prefer the traditional approach, you can follow along using MPLAB IDE. The steps are exactly the same. Also, make sure you have the latest version of MCC installed before following along. I am going to open Visual Studio Code MPLAB Extension and create a new project. Click on this new project icon to create a new project. Now we need to give a name for the project. I will name it dsPIC33 PWM and press Enter. Next, select the project location. Here I am choosing a custom location for my project folder. Now we need to select the target device. I am using the dsPIC33 CH512MP508, so search for it and select it from the list. Next, we have the option to use a pre-built project template, but here, I will just go with the standard new application template. Then we need to select the toolchain. I am going to use the latest XC16 Compiler, version 2.10. Now we need to open MCC Melody to configure the peripherals. Press Ctrl+Shift+P to open the command palette, then search for MPLAB MCC Launch and select it. If you have an existing MCC configuration file, you can load it from here, but I will create a new MCC configuration from scratch. Next, select the current project location for the configuration. Next, you will see 2 options, default and more options. We can proceed with the default values, but since we need to apply some specific settings for the PWM, I will go with more options. Give a name for the configuration file. I will name it SRC. Then select the location. I will point it to the same project folder. You can choose a custom location if you prefer, but it is always a good practice to keep the configuration inside the same project folder. Now give it a moment to load MCC Melody. Alright, MCC Melody is now loaded inside Visual Studio Code. Let's start configuring the settings. First, let's set up the system clock. In the Project Resources panel on the left, look under the System section and click on Clock Control. The clock configuration panel will appear on the right-hand side. Here we need to select the system clock source. Now, you could use the internal FRC oscillator for a simple example like this, and it would work just fine. However, if we look at the development board schematic, we can see that the board comes with an onboard 8 MHz oscillator connected to the RB0 pin, which is the OSCI input pin of the microcontroller. So, to match our hardware, I will set the clock source to the primary external oscillator. Once you select that, if you open the pin view, you will notice that the RB0 pin is automatically configured as the clock input pin, which confirms our selection is correct. Now, for this example, I am not going to enable the PLL. Since we are just demonstrating basic PWM, the external 8 MHz oscillator is sufficient. This means our system clock will run at 8 MHz, and the peripheral clock, which drives the PWM module, will be 4 MHz, half of the system clock. Alright, that covers the clock configuration. Let's move on to the PWM settings. Now, open the Device Resources panel. Under the Drivers section, find PWM and click the plus icon to add it to your project. Once added, go back to the Project Resources panel, and you will see the PWM driver is now listed under your project peripherals. Let's configure the PWM settings. First, we need to select the PWM PLAB selector. I will select SCCP1. Now, you might be wondering, what is SCCP? If we open the dsPIC33 family datasheet and search for SCCP section, we can find the explanation. SCCP stands for Simultaneous Capture, Compare, and PWM Timer Module. It is a flexible timer peripheral that can be used for input capture, output compare, and PWM generation. I recommend reading this section of the datasheet to get a deeper understanding of all the available settings and register configurations. But for now, let's configure everything using MCC Melody. Here we can assign a custom name to our PWM instance. I am happy with the default name PWM1. Now, under Configuration Settings, first check the Module Enable checkbox to activate the module. For our first example, we need a frequency of 10 kHz and a duty cycle of 50%. Let's enter those values now. Here, requested frequency is 10 kHz, and the calculated one also 10 kHz. Duty cycle is 50%. Next, we need to select the sync and trigger source. If you open the drop-down, you will see several options available. I am not going to go through every single option in this video, but I have added a detailed explanation of each one in the README file. So please check that out if you want to understand all the available sources. For this example, we do not want to trigger the PWM from any external or internal source, so I will set it to none. Setting it to none means the PWM runs completely free. It uses only its own internal timer, starts immediately when enabled, and no external event controls it. Next is the sync and trigger mode selection. Again, I have added the full explanation in the README file. But it's simply, sync keeps the PWM running but locks its period edges to the source signal. And trigger works like a gate. The PWM waits until the trigger event arrives, then starts. Here I will just leave it set to sync. Next is the interrupt-driven setting. For examples 1, 2, and 3, we do not need interrupt-driven PWM, since the PWM hardware generates the signal automatically without any CPU involvement. So I will leave this unchecked for now. Alright, that covers the PWM module settings. But before we generate the code, we need to assign the PWM output pin. Open the Pin Manager view and assign RD0 as the SCCP1 output pin. I have connected this pin to my logic analyzer, so we can verify the PWM output waveform after programming. Now, one more important thing before generating the code. Since I am using the PICkit 5 with the master-slave programming and debugging interface on this development board, I need to update the ICD settings. Go to the ICD settings and change the emulator pin placement to communicate on PGC2 and PGD2. This makes sure the debugger communicates on the correct pins for this board. Alright, all settings are done. Let's go ahead and generate the code. Now, if we look at the output panel at the bottom, we can see that the MCC code generation was successful. Let's explore the generated files. If we open the MCC folder in the project, we can see the main file is there. And inside the MCC generated files folder, we can find all the peripheral configuration files. Let's open the SCCP1.c file. Inside this file, find the PWM initialize function. This function handles all the register-level initialization based on the settings we configured in MCC Melody. Let's take a closer look at what was generated. At the top, we have the control registers. You can look up the meaning of each bit in the dsPIC33 family datasheet under the SCCP module register description section. Then below that, we have the timer and compare value registers. Again, the datasheet explains each of these registers in detail. Now, let's focus on the two most important values here. The first one is PRL, which is set to 400. The second one is CMPB, which is set to 200. Let me explain what these values mean. Let's open the README file for this project. I have added a full explanation of how the PWM calculation works. Our system clock is running at 8 MHz. The peripheral clock is half of that, which gives us 4 MHz. To generate a 10 kHz PWM signal from a 4 MHz clock, we need to divide 4 MHz by 10 kHz, which gives us 400. So the PRL register, which is the period register, is correctly set to 400 by MCC. This means the PWM counter counts from 0 up to 400 and then resets, giving us exactly 10 kHz. Now, the CMPB register is set to 200. What does that mean? We set our duty cycle to 50%. 50% of 400 is 200. So CMPB, which is the compare register that controls the duty cycle, is correctly set to 200 by MCC. The PWM output stays high from count 0 to count 200 and stays low from count 200 to count 400. That gives us exactly 50% duty cycle. So MCC has correctly calculated and configured all the register values based on what we set up: 10 kHz frequency and 50% duty cycle. All right, let's see this in action. First, let's build the project. Open the MPLAB Extension panel on the left side. You will see the Build button. You can click that to compile the project. Or, if you want to debug the code and set breakpoints, you can click the Start Debug button. But if you just want to build and program the device directly, you can simply press Ctrl plus F5. Since I have not set any breakpoints for this example, I will just build and download. So I will press Ctrl plus F5. On the first build, you will be asked to select the debugger configuration. Select the MPLAB debugger. Make sure to select the correct toolkit, in my case, PICkit 5. Give it a moment to build and upload the program to the device. Build was successful and program uploaded. Now let's verify the output. I have connected the RD0 pin to my logic analyzer. Here, we can clearly see the PWM signal on the screen, 10 kHz frequency with a 50% duty cycle, exactly as we configured in MCC Melody. The signal period is 100 microseconds, and the pulse is high for 50 microseconds and low for 50 microseconds, which confirms our PRL value of 400 and our CMPB value of 200 are working correctly. Now let's quickly look at example 2, 10 kHz with 30% duty cycle. If we open the README file, we can see all the calculations laid out clearly. For this example, we only need to change one value, the CMPB register. Our period is still 400 counts, giving us 10 kHz. We are not changing the frequency, only the duty cycle. 30% of 400 is 120, so CMPB should be set to 120. In hexadecimal, 120 is 0x78. That is the value we expect to see in the generated code. But instead of manually editing the register value, let's go back to MCC Melody and edit it there. Open the PWM settings and change the duty cycle from 50% to 30%. Then regenerate the code. Now let's open the SCCP1.c file and look at the CMPB value inside the initialize function. And there we go. CMPB is now correctly updated to 120. This confirms that MCC Melody is correctly translating our percentage-based settings into the proper register values. Now let's build and download the program. Press Ctrl plus F5. Let's check the logic analyzer output. And we can clearly see the PWM signal has changed. The signal is high for 30% of the period and low for the remaining 70%, exactly as we configured. Now let's move on to example 3, 100 kHz with 40% duty cycle. Let me show you the calculation first. our peripheral clock is still running at 4 MHz. To generate 100 kHz from a 4 MHz clock, we divide 4 MHz by 100 kHz, which gives us 40 counts. So PRL should be set to 40. Now for the duty cycle, 40% of 40 is 16. So CMPB should be set to 16. Now, for this example, instead of going back to MCC and regenerating, I am going to directly edit the values inside the SCCP1.c initialize function. Save the file. Now press Ctrl plus F5 to build and download the program. Let's check the logic analyzer output. And there we go. We can clearly see the PWM signal running at 100 kHz with a 40% duty cycle. The signal is high for 40% of each period and low for the remaining 60%. All right, now let's move on to example 4, PWM using DMA. In the previous 3 examples, the PWM duty cycle stayed the same throughout the entire program, a continuous fixed-width signal. In this example, I am going to show you something more interesting. We are going to automatically change the duty cycle on every single PWM period, without any CPU involvement. To do that, we are going to use a DMA channel. Let's see how to set this up. First, open MCC Melody. Before adding the DMA driver, I need to make one important change to the clock configuration. Go to the clock settings and change the system clock source to the external oscillator with PLL enabled. For the DMA to work correctly with our PWM timing, we need the PLL enabled to run at a higher clock speed. Now set the system frequency to the maximum value by enabling that option. This gives us a system clock of 180 MHz and a peripheral clock of 90 MHz. This is an important difference from the previous 3 examples. In examples 1, 2, and 3, our peripheral clock was only 4 MHz because we were using just the external 8 MHz oscillator without PLL. Now with PLL enabled, our peripheral clock is 90 MHz. So keep that in mind. All the register values we calculated earlier will now be different because the clock driving the PWM module has changed. We will go through the new calculations when we get to the code section. Now go to the Device Resources panel, find the DMA driver, and click the plus icon to add it to the project. Once added, go back to the Project Resources panel and open the DMA settings. You can assign a custom name to the DMA instance if you want, but I will keep the default name. Now, if you open the datasheet of the dsPIC33 and navigate to the DMA module section, you can find detailed explanations of all the settings and register configurations. You can also find the different DMA transfer methods and memory region descriptions there. Now, if you are not familiar with DMA, direct memory access, please leave a comment below. I will create a dedicated video to explain how DMA works in detail. For this example, we are going to use direct memory to register data transfer, copying duty cycle values from an array in RAM directly into the PWM duty register automatically on every PWM period. All right, let's go back to MCC and configure the DMA settings. At the top of the DMA settings, you will see the DMA memory region limits, the lower and higher address boundaries. I will keep these as default. We are only transferring a small amount of data, so the default region is more than enough. However, if you are working with multiple peripherals using DMA simultaneously, make sure to carefully plan your memory regions and always refer to the datasheet. Now, we have multiple DMA channels available. I will use channel 0 for this example. Go ahead and enable channel 0. Now let's go through each setting one by one. The enable reload. I will leave this unchecked. We will handle the repeat behavior manually in code, which gives us more precise control over the timing. Next, transfer mode. Here we have 4 options. One-shot transfers a fixed number of values once and then stops. Continuous keeps transferring indefinitely without stopping. Repeated one-shot is similar to one-shot, but restarts automatically. And repeated continuous is like continuous, but with automatic reload. For this example, I will select one-shot. The DMA will transfer all our duty cycle values once per trigger sequence, and we will manually restart it in code after each complete cycle. Next one, the trigger source. This tells the DMA what event should trigger each individual transfer. We want the DMA to load a new duty cycle value at the end of every PWM period. So I will select main SCCP1 OC/IC event. This means every time SCCP1 completes one PWM cycle, it fires a trigger, and the DMA automatically loads the next duty cycle value. No CPU required. Next, source address mode. I will set this to increment. This tells the DMA to step forward through our array automatically, reading index 0 on the first trigger, index 1 on the second trigger, index 2 on the third, and so on. If we left this as unchanged, the DMA would read the same value from index 0 every single time, and the duty cycle would never change. Next, source address. This should point to the starting address of our duty cycle array in RAM. However, we cannot hardcode this address here in MCC. The reason is, the array address in RAM is assigned by the compiler and linker at build time. It can change every time we rebuild the project. So I will leave this as 0 for now as a placeholder, and we will set the correct address in code before starting the DMA. I will show you exactly how to do that in the code walkthrough. Next, destination address mode. I will set this to unchanged. The destination is always the same register, the PWM duty register. It never moves, so we do not want the DMA to increment the destination address. Next, destination address. This is the most important setting, so let me explain it carefully. Our goal is to change the PWM duty cycle on every period automatically. If you remember from the earlier examples, the duty cycle is controlled by the CMPB value, which maps to the CCP1RB register inside the SCCP1 module. So the destination address must point directly to that register. Let's open the datasheet and search for CCP1RB. Here we can find the register description, and the register address is 0x96C. So I will enter 0x96C as the destination address. This means every single DMA transfer will write directly into the PWM duty register, changing the duty cycle instantly, with absolutely zero CPU involvement. Next, data size. I will select 16-bit. Our duty cycle values are stored as unsigned 16-bit integers. And the CCP1RB register is also 16-bit. These must always match. Next, transfer count. I will set this to 9. Now you might wonder, why 9? If we have 10 duty cycle values? This is because the transfer count register on the dsPIC33 DMA is 0 indexed. A value of 0 means 1 transfer. A value of 9 means 10 transfers. So setting it to 9 gives us exactly 10 transfers, covering all 10 duty cycle values in our array. Next, interrupt driven. I will enable this. When the DMA finishes all 10 transfers, it will fire an interrupt callback function in our code. We will use this callback to reset the source address and rearm the DMA for the next cycle, which is exactly how we achieve the continuously repeating staircase pattern. Alright, those are all the DMA channel settings. Now let's go back to the PWM settings. The frequency stays at 10 kHz. For the initial duty cycle, I will set it to 10%. But keep in mind, the DMA will override this immediately as soon as the first PWM period completes. Also, I will enable the interrupt-driven mode in the PWM settings as well. I want to show you one additional feature using this interrupt. Now, before generating the code, go to the pin manager and set the RD2 pin as a GPIO output. I am going to toggle this pin inside the SCCP1 interrupt callback function. I will show you exactly why this is useful and what it looks like on the logic analyzer when we get to the code section. Alright, all the MCC settings are now configured. Before generating the code, I will delete the previously generated MCC folders to make sure we start fresh with a clean configuration. I will delete the PWM folder and the system folder from the MCC generated files directory. Now let's generate the code. Give it a moment to complete. Alright, the files are now generated successfully. Let's take a quick look at what was created. First, open the DMA.c file. Inside the DMA initialization function, you can see all the DMA channel settings we configured in MCC have been correctly translated into register-level code. Now let's open the SCCP1.c file. Look at the initialize function. You can see the PRL value is now 9000, and the CMPB value is now 900. This is different from example 1, where PRL was 400 and CMPB was 200. The reason is our clock change. In examples 1, 2, and 3, the peripheral clock was 4 MHz. To get 10 kHz, we needed to divide by 400. Now with PLL enabled, the peripheral clock is 90 MHz. To get 10 kHz from 90 MHz, we divide 90 MHz by 10 kHz, which gives us 9000. So PRL is correctly set to 9000. And for the initial 10% duty cycle, 10% of 9000 is 900. So CMPB is correctly set to 900. These are exactly the values we expect. MCC has correctly recalculated everything based on the new 90 MHz peripheral clock. Alright, now let's write the code. Open the main.c file. Now, you may notice that the C and C++ IntelliSense and Visual Studio code is not recognizing the system header files correctly. The include paths are not configured yet. To fix this, I have already prepared a SCCP properties JSON template file. I will copy that into the .vs code folder of this project. I will also upload this template file to the GitHub repository, so you can just grab it from there and use it directly in your own projects. Alright, now let's write the code. Let me open the README file first. I have already prepared all the code snippets there, so we can simply copy them into the main.c file. First, we need to declare the PWM duty cycle array. The array starts at 900 and increases in multiples of 900. The reason is, our PER is now 9000 for 10 kHz at 90 MHz peripheral clock. 10% of 9000 is 900. So each step of 900 represents a 10% increase in duty cycle. The array goes from 900 up to 9000, covering 10% all the way up to 100% in 10% steps. Now inside the main function, the first thing we need to do is set the DMA source address to point to our array. The source address register is DMA src0. We set it like this. DMA src0 equals the address of PWM data index 0. Alternatively, MCC also generates a helper API function called DMA_source address set. You can use that instead if you prefer to keep things consistent with the MCC generated code style. Next, I have also added the destination address setup here in code, even though we already configured it to 0x96C in MCC. It is good practice to set all DMA parameters together in one place in your code. This makes it much easier to read and maintain, especially when you come back to the project later. You can also use the DMA_destination address set API function for this, just like the source address. Next, I have set the transfer count here in code as well. Again, we already set this to 9 in MCC, but keeping it here makes the code self-contained and clear. Then we enable DMA channel 0 to arm it and make it ready to receive triggers from SCCP1. Then this callback function, SCCP1 PWM callback function. Inside this function, I am toggling the RD2 GPIO output pin. So every time SCCP1 completes one PWM period, this pin toggles high, then low, then high, and so on. Now you might ask, why do we need this? When we connect RD2 to the logic analyzer alongside the PWM output pin, we can clearly see the PWM period boundaries on the screen. This makes it much easier to verify that the DMA is loading a new duty cycle value at exactly the right moment. at the start of each new PWM period. It is a very useful debugging technique when working with DMA and PWM together. Alright, let's copy all of this code into our main.c file. First, necessary headers. Then copy and paste the codes. Okay, save the file. Now let's build and upload the program. Press Ctrl plus F5. Give it a moment to compile and upload. Build successful. Okay, now program is uploading to the device. While the upload is finishing, let me start the logic analyzer capture. And there we go. We can see the PWM pulses have started. Let me stop the capture and zoom in on the signal to get a better look. Now we can clearly see the first few cycles of the PWM output. The pulse width is visibly changing on every single period, exactly what we wanted. Let's look at channel 1 as well. Channel 1 is connected to the RD2 pin. We can see it toggling every 100 microseconds. That is our SCCP1 PWM callback firing on every PWM period boundary. And if you look carefully, every time channel 1 toggles, the duty cycle on the PWM output updates to the next value. This confirms that the DMA is loading a new duty cycle value at exactly the right moment, at the start of each new period. Now, you might notice something interesting here. After the 90% duty cycle, the pattern stops updating and stays continuous at the same width. Also, the last duty cycle in the pattern is 90%, not 100% as you might expect. Now, this is not an error. This is actually normal and expected behavior. Let me explain why. In our current code, we have not added a DMA callback function yet. So after all 10 transfers complete, the DMA simply stops and goes idle. There is nothing to reset the source address or re-enable the DMA channel. Now, you might ask, we have 10 values in our array, and the last value is 9,000, which is 100%. So why is the signal staying at 90% and not 100%? Here is what is actually happening. Remember, our transfer count is set to 9, which means 10 transfers, 0 indexed. So the DMA transfers all 10 values correctly. However, look at the timing carefully. The DMA loads each new value into CCP1 RBL at the moment the SCCP1 trigger fires, which is at the start of a new PWM period. When the 10th transfer loads 9,000 into CCP1 RBL, that new duty cycle value only takes effect from the next PWM period onwards. But there is no next period for the DMA. It has already finished and gone idle. So the PWM counter is currently midway through the period that was set up with 8,100, which is 90%. That period completes normally showing 90%, and then from the next period onwards the duty register holds 9,000. That is 100%. But by the time that 100% period starts, the DMA is already idle and no more updates happen. So what you are seeing on the logic analyzer is the 9th value of 90% completing its full period visibly, and then the signal locking at whatever the last loaded value was. This is a classic DMA and PWM period boundary timing behavior. In the next step, I will add the DMA callback function to reset the source address and re-enable the DMA, so the full pattern from 10% to 90% repeats continuously. Now let me add the DMA callback function. Inside the callback, we reset the source address back to the start of the array, reset the transfer count back to 9, and re-enable DMA channel 0. This way, after every complete cycle of 10 transfers, the DMA automatically resets and waits for the next SCCP1 trigger to start the pattern again from 10%. However, just adding the callback alone is not enough to make the pattern repeat continuously. We also need to update two settings in MCC. Open MCC Melody and go to the DMA channel 0 settings. First, enable the reload checkbox. Second, change the transfer mode from one-shot to repeated one-shot. With these two settings combined, the DMA hardware will automatically reload the transfer count and source address after each complete cycle, working together with our callback function to ensure the pattern repeats seamlessly. Before regenerating the code, I will delete the previously generated DMA folder to make sure we get a clean, fresh generation. Now regenerate the code. The DMA initialization function is now updated with the new reload and repeated one-shot settings. Let's build and upload the program again. Press Ctrl plus F5. Build successful, program uploading. Let's start the logic analyzer. We can see the PWM signal has started. Let me stop the capture and zoom in. Now we can clearly see the PWM pattern is repeating. The duty cycle steps up from 10% to 90% and then resets back to 10% again. The pattern is continuously looping. But you will notice, it is still going from 10% to 90%, and the 100% step is still not visible. The pattern reloads right after 90%. Let me explain why this is happening. When the DMA completes the 10th transfer, loading 9000, which is 100%, into SCCP1 RBL, the reload mechanism and the callback function both activate at almost exactly the same moment. The reload resets the source address back to PWM data index 0, and the callback also resets DMA SRC0 back to the start of the array. The problem is timing. The 100% value gets loaded into SCCP1 RBL at the start of a PWM period. But before that period has a chance to complete and show a full 100% pulse on the oscilloscope, the very next SCCP1 trigger fires, and the DMA immediately loads PWM data index 0, which is 910%, overriding the 100% value before the period finishes. So the 100% duty cycle exists for less than one full PWM period, too short to be clearly visible as a separate step on the logic analyzer. This is a direct result of the DMA reload and callback happening at the PWM period boundary. The reset is so fast that the last value gets overwritten before it can be observed. To fully fix this, we would need to introduce a one-period delay before rearming the DMA, allowing the 100% pulse to complete fully before the pattern resets to 10%. But for the purpose of this tutorial, this behavior is a great real-world example of DMA and PWM boundary timing interactions, and understanding this is very valuable when you start working on more advanced projects like motor control or LED dimming profiles. Alright, that is it for today's video. We covered 4 PWM examples on the dsPIC33, starting from a simple fixed duty cycle output, all the way up to DMA-driven automatic duty cycle updates. If you have any questions, feel free to ask in the comment section below. I will do my best to answer every one of them. In the future, I will be creating more dsPIC33 tutorials like this one, covering more peripherals, more examples, and more real-world embedded applications. So if you found this video helpful, please give it a thumbs up, leave a comment, and subscribe to the channel so you do not miss any upcoming videos. Thank you for watching, and I will see you in the next one.